In this next portion of Lesson 6, as we learn about binomial distributions, I want you to take a look again at the diagram I drew with flipping 4 coins and the different number of ways that those 4 coins can come out. Now, as we did this, we noticed that there was 1 way for us to get 0 heads, 4 ways to get 1 head, 6 ways to get 2, 4 to get 3, and 1 way to get 4 heads. Now, as you look at those numbers, 1, 4, 6, 4, 1, some of you might be recognizing those as being the same as the 4th row of Pascal's triangle. Now, if you remember in that row of Pascal's triangle, the other way to get the numbers that made up Pascal's triangle was to use combinations. So if I wanted to find this 1, that would be the same as taking 4C0, 4C1, here's 4C2, here's 4C3, and here's 4C4. So those matched up with the number of different ways to choose 0 from 4, 1 from 4, 2 from 4 different objects. Now, keeping that in mind, the next portion of our lesson is looking at binomial distribution. So, one type of probability distribution is a binomial distribution. A binomial distribution shows the probabilities of the outcomes of a binomial experiment. So a binomial experiment must meet the following conditions. First of all, there are n independent trials, meaning that each trial that we do is independent from the other. It doesn't affect the other, such as flipping 4 coins. You flip a coin, you come up heads, that doesn't affect the flipping of the next coin in any way. The next, each trial has only 2 possible outcomes. There's either success or there's failure. With the flipping of the coin, it's an easy one because it's either heads or tails. It's one or the other. There's not a 3rd or 4th option. There's just 2 options. You either get what you want or you don't, period. Now, the probability of success is the same for each trial. This probability is denoted by P, and then the probability of failure would be the complement to that, which would be 1 minus P. So those probabilities would have to add up to 1. They're complements of each other, again, because there is no 3rd or 4th option. There's just the 2 things. There's either success or failure. There's either heads or tails. You either get the right number or you don't. That's it. If we have a binomial experiment, then the probability of getting exactly k successes in n trials is equal to this formula that you see right here. Oh my goodness. So this NCK, you'll notice, first of all, here would be the number of different ways for that item to happen. The number of ways for us to flip 2 heads out of 4 coins, or whatever it might be. So that NCK number is that same number that we would have used from Pascal's triangle. Then I have P to the k power. P is the probability of success, and then 1 minus P, remember that's the complement to that. Here's the probability of failure. I raise P, the probability of success, to the k power, which is the number of times that I want to be successful, times 1 minus P, the probability of failure, raised to the n minus k power, which is the other options. So we're going to use this formula in a couple of different examples right now. Our first example, suppose you flip 6 coins this time. We're going to apply the binomial distribution formula above to find the probability of flipping exactly 4 heads. So the probability of flipping exactly 4 heads out of those 6. So a couple things. When I do these problems, I like to write some things down because I've got all sorts of variables involved in the formula. So first of all, I'm going to just jot down, okay, what's n? N is the number of trials. Well, in this case, I'm flipping 6 coins, so n is 6. There's 6 trials going on here. P is the probability of success. Well, I want heads. What's the probability of flipping a coin and getting heads? Well, it's 1 out of 2. And if you prefer to work with decimals, you could have a 0.5 there instead. Now, 1 minus P, the probability of failure. Well, 1 minus 1/2 is also 1/2, or 0.5. So those numbers are going to be the same. Now, the other thing I need to identify is K, the number of successes. So the number of success to me in this case is 4. I want 4 heads out of the 6 coins that I flipped. So K is equal to 4. Now, given all of those different things, I can use my formula. I'm going to find the probability of exactly 4 heads. Well, that's going to equal. Start off with the NCK business. So that coefficient that comes from Pascal's triangle. Well, I've got 6 trials, and I want 4 heads. So 6C4 is what I start with. Whatever that is, I'm going to multiply that times the probability of success, which in this case is 1/2 or 0.5, raised to the k power. The k power, again, is the same as it is here. Well, there's 4 different coins that I want to be heads. Times 1 minus p, well, the probability of failure in this case was also 0.5. I raise that to the n minus k power. The n minus k power would be 6 minus 4. Now, obviously, that's going to be 2. So, at this point, I resort probably to my calculator. I evaluate the combination of 4 objects chosen from 6, and I get 15. I take 1/2 raised to the 4th power, and I get 1/16. And again, I'm flipping back and forth from decimals to fractions. You can use either one, doesn't matter. It's whatever you're most comfortable with. And then I take 1/2 raised to the 2nd power, 1/2 squared, well, that's going to be 1/4. Again, from a decimal to a fraction, you can use either one, whichever you're most comfortable with. And then I multiply these things together. 15 times 1/16 times 1/4. Well, if I wanted it as a fraction, it would turn into 15 out of 64. Sometimes fractions are great, they're easy to work with. A decimal would be just fine here as well. And if you were to type in the expression, right here, or even type it in like this, if you're very careful with your parentheses and things like that, if you type in this whole expression and get a decimal, that decimal that you would get would be rounded to 3 decimal places, would be 0.234. So that's, again, an approximation, but either of these would be acceptable answers, my decimal or my fractions. There's the probability of getting exactly 4 heads if you're flipping 6 coins. We're going to do one more similar example here, just to show you what it's like when the probabilities of success and failure are a little bit different. So, if you spin the spinner right here 8 times, what's the probability of landing on purple exactly 3 times? Well, my formula again that I'm going to use here, because this is, again, even though there's 4 options, this is still a binomial experiment, because I have 2 items. It's either purple or not. It's either purple or it's not purple. Okay? That's a binomial experiment. So, that being the case, I can use my formula from before. NCK times p to the k power times 1 minus p to the n minus k power. So let's identify some different things that we're going to plug into this formula. First of all, n, the number of trials in this case, is 8, because I'm going to spin the spinner 8 times. K, the number of successes, is going to be 3, because there's exactly 3 times is what I would like. P, the probability of success. In this case, again, I look at it and say, okay, well, there's 4 items, but success to me is getting purple. Success to me is getting 1 out of those 4 options. So my probability of success is 1/4, or again, if you want to use decimals, 0.25. Which means that the probability of failure then, the complement to that would be 3/4 or 0.75. Make that a little better. 3/4 or 0.75. That's what I would need to then find the probability of this particular idea going on. So the probability of 3 purples, we'll say, is equal to NCK. So we start with this. We start with 8C3, combination of 3 items chosen from 8, times the probability of success, which in this case is 0.25, raised to the k power. Well, k is 3 again, so cube that, times the probability of failure, which is 1 minus p, or 0.75. Raise that to the n minus k. Well, n minus k, that's 8 minus 3, so I'm going to go ahead and put that as 5, rather than writing 8 minus 3. So I have 3 successes, 5 failures, is kind of the way to think about that, times the number of ways that that could happen. I evaluate all of these expressions on my calculator. I take 8C3 and I get 56. 0.25 cubed is going to be 1/64, and 3/4 to the 5th. You know what? Forget about it. You're probably just going to type this whole thing in all at once. Again, as long as you're careful, or if you type them in separately, the answer you're going to end up with in the end, as a fraction, be 1701 over 8192. It's a lot. Probably more realistically, you're going to have a decimal answer that you're going to keep it as, and that decimal would be approximately 0.2076. So here's our probability of getting it exactly 3 purples if I spin that spinner 8 times. So there's a second example of a binomial experiment, a binomial distribution, and the probability of the different events occurring.